My name is Noah Misch. To give you a little background about myself, I'm a PostgreSQL committer and an Enterprise DB employee. And I'm here today to talk about the PostgreSQL operator class facility. Operator classes are part of the provision PostgreSQL has made for its users to extend the PostgreSQL indexing capabilities. So I'll also be talking about a few other aspects of PostgreSQL indexing that interact with operator classes heavily. Then we'll take a close look at the SQL used to define operator classes. I'll discuss the implications of some of the design choices you can make when defining your own operator classes, and discuss those in the context of some familiar data types. While operator classes did originate in the context of indexing, the system now uses them in several other areas. So I'll go through those so that you're aware of them. Then finally, I'll be talking about the implications for the software you write and how you can make sure that your software makes the assumptions that it's entitled to make and no more. One of the hallmarks of PostgreSQL in general is its extensibility, and this is particularly strong in the context of its indexing capabilities. There are two relevant layers there. The first is the index access method layer, and the second is the operator class layer. The index access method layer, currently there are 5 index access methods. These are btree, hash, gist, gene, and spgist. It is theoretically possible to add your own as a user, but in practice they've mostly been added to the core code as part of major releases. Some of you may have seen a talk just the last slide about a proposal to add a new index access method. So expect that list to grow in the future, but in the context of one major release, that's the list as it stands today. Now, in order to index values of a particular data type, the system requires certain knowledge particular to that data type. The index access methods do not know about specific data types. Instead, they consult a database object called an operator class to get the data type specific knowledge they need in order to index values of a particular data type. Now, in contrast, user extension in this area is quite alive and well. If you find an extension that adds a data type in a place like the PostgreSQL contrib area or PGCon, you'll regularly find that they include additional operator classes. So that flexibility definitely being used in the field today. What is an operator class? It's glue between an index access method and a data type. It provides the index access method with the operations it requires on that data type and the facts it requires in order to do the full task of indexing values of that data type. Specifically, that glue consists of functions and operators, the details of which are specific to each index access method. Now, for most of this talk, I'll be focusing on the btree index access method. That is the most prominent. It's the default if you issue a create index statement without specifically naming a different index access method. It's also the only one that supports uniqueness, so it's the only one used in primary key constraints and unique constraints at this time. But if we have some extra time at the end, I'll go into a couple of other access methods a little bit. So to give a bit of background on how btree works, it creates a data structure on disk that boils down to a method for maintaining a sorted list. And it does so in a way that's relatively efficient in the face of concurrent modifications, concurrent indexes and updates to that list. So the data type specific information required by btree is a function that's able to place objects of the data type in order, a comparison function. The function takes 2 arguments of the data type in question, returns an indication of whether the first of the arguments is less than, equal to, or greater than the second argument. We consider these SQL statements here. Each of these makes some reference to operator classes in order to do its job. When you issue the create table statement that requests a primary key, the system looks up what's called the default btree operator class associated with the data type of that column. And It associates that operator class with the index it creates in order to implement this constraint. Then, whenever you insert new rows into a table, of course, you must create new index entries for each of those rows. So when the first insert statement runs, it's creating the first row in the index. There's no need to compare anything. Since the job of this B-tree index is to maintain the values found in that column in order, when the system executes the second insert, it has to decide, does January 1st, 2015 come before or after January 1st, 2014 in the index? It's the comparison function found in that operator class that has the knowledge that January 1st, 2015 is to be considered greater than January 1st, 2014. And what happens when a query runs? Well, the query planner looks at the operators that appear in a where clause, and it examines their membership in operator classes to find opportunities to use index scans to satisfy the query. In this particular query, that less than operator happens to be a member with the same operator class used in the index that implements the primary key. It's that observation that tells the planner that an index scan on that index can possibly satisfy this query. There's a tightly related concept to operator classes called operator families. And their role is to extend the operations that operator classes do to cover situations that involve more than one data type. When you're indexing, you're only dealing with one data type, because a particular column has a particular data type, and that's a long-term thing. However, when you're actually searching in an index, the search condition may or may not be of that exact same data type. And operator families add in the concept of comparing between different data types. So consider the slight modification to the queries we saw in the previous slide. There's an operator family called date-time-ops, which ties together all the comparisons between three data types, the date data type and the two timestamp data types. And as a result of the existence of that operator family, the system knows that it can search through an index that was originally done on a date value using a timestamp search condition. Now, this is the SQL statement used to create an operator family and then create an operator class. This here is simply a mimic of an operator class that already exists in the base system, namely the default B-tree operator class for the integer data type. After some preliminary material that specifies the name and the data type and the access method to which this applies, the bulk of the material is a list of functions and operators with associated ordinal numbers. Now, the ordinal numbers that you would expect to appear depend on the access method. This is what is typical for B-tree. There's one mandatory function entry and 5 mandatory operator entries. The function entry is always that comparison function I mentioned earlier. It takes two values of the data type, tells you whether the first is less than, equal to, or greater than the second value. That's used to actually maintain the index, to actually find where a new row belongs relative to the other rows that already exist in that index. The 5 operators are used for a different role. They're used to decide when a particular query can use that index, when a particular where clause is applicable to search in that index. Now, these 5 operators are expected to have the mathematical properties of a total order relation. That is to say, each of them must be transitive, and given 2 input values, you must get a true result from either operator 1 or operator 3 or operator 5, and a false result from the other 2 of them. If you were to say, have operator 1 and operator 3 return true, indicating that the values are both less than and equal to each other, that would be an error in the definition of the operator class. Now, it may seem kind of redundant to have to explicitly say that the operator that looks like an equal sign is in fact an equality operator. Well, it turns out that the system otherwise does not make too many assumptions about the behavior of an operator based on its name. As far as the rest of the system is concerned, you can create an operator that's named with the equal sign and have it do multiplication, and the system has no problem with that. It's when you actually specify operators in a create operator class statement that the system is now given liberty to assume that these have the mathematical properties that you'd expect of comparison operators. So for the rest of this talk, I'm going to use a couple terms fairly carefully. When I refer to the equal sign operator, I am specifying the operator whose name consists of a single equal sign, regardless of the behavior of that operator. And when I use the term equality operator, I'm referring to an operator, regardless of its name, that behaves like a mathematical equality comparison. Now, when you look at it in this context, you see that the create operator family statement is pretty trivial, and the create operator class statement is where all the interesting things happen. One thing to be aware of is that once this statement is done executing, the system catalog entries have a different focus. The system catalog entries are focused on the operator family. So each of those operator lines will create an entry in the PGAM op catalog, and any function line would create an entry in the PGAM proc catalog. Those will actually be tied up to the operator family, and the operator classes are sort of treated like leaves off the operator family. This sort of discrepancy between the organization of the SQL and the organization of the catalogs is probably a historical one. Operator families were introduced in 8.3, whereas operator classes have been in the product since the beginning, more or less. So when operator families were introduced, the catalogs changed more than the SQL syntax changed. The system does not limit you to a single operator class for each data type and access method. And if you define more than one, you can only define one of them as being the default, but you can define the others. And they represent, in the context of B-tree, alternative sort orders for a particular data type. Now, for some data types, this is kind of a hard concept to imagine. I mean, integers have one natural sort order. Now, you could do something crazy, like order by the number of 1 bits in its representation or something like that, but you really have to kind of strain to think of another way to sort integers that's not just silly. But a data type where there are multiple valid sort orders is the polygon data type. So consider these 3 shapes here, and imagine we created a table with a polygon column and entered the vertices of these shapes into polygons in that column. Who'd like to venture a guess of which of these 3 shapes is going to be considered greatest according to the greater than operator when applied there? Kevin?
The triangle.
Triangle's going to be greatest? Yes. Why do you think that?
Because it's got the greatest area.
Okay. Well, anyone else want to guess? Andres?
The square, because it has the highest center point.
Another good guess.
The other one.
Dr. Gunn.
It's green.
Vic. And why is that, Vic?
It has the largest number of sides.
Well, all very true observations. No, it's actually a trick question.
And it's green.
There is no greater than operator.
That's right. There's an equality operator.
There's an equal sign operator.
There's an equal, excuse me, you're right. An equal sign operator that works on it.
Yeah, but you all thought of pretty much the kind of comparisons that that I think are credible for these, and you can compare by perimeter as well, things like that. And this also comes up in the natural world. Questions like, what is the largest lake? Well, Lake Baikal is the largest volume, Lake Superior has the largest area. You can even come up with exotic measures like longest surface diagonal, in which case Lake Tanganyika is the largest.
How do you know that?
That's why he's speaking and we're sitting.
I'm mainly a hydrologist. I just think about this stuff sometimes. And, this flexibility is not something that's actually used too much in the core code. One example of it being used is a non-default operator class called text pattern ops. This is a bit obsolescent even since 9.1 introduced the collate keyword, but it existed for a long time and still exists for backward compatibility to support the optimization of the like operator. I think one reason that it hasn't been popular to have non-default B-tree operator classes is that you need a different list of those 5 operators for each one of them, or at least about 4 of them. Sometimes you can reuse the equality operator, but you need a new less than operator. The trouble is that in order to have two less than operators that take the same data type, they either need to have different names, as in not actually be the less than symbol, or they need to be in different schemas. So there's really only one operator name people like to use when they're talking about less than, and that's the less than operator. So I think that's been a barrier to sort of exploitation of this feature. And a similar problem affects hash indexes. Where it's not a problem is for all the other operator classes. Gene and GIST and SPGIST don't have this problem that you necessarily need to use different operator names in each operator class. Hopefully, if we have extra time, I'll get into that a bit more, but basically, those operator classes give the person defining the operator class more control over structural aspects of the index so that you can, for example, have 2 operator classes supporting the exact same operators, but with different performance characteristics. That's not something that arises in the context of B-tree or hash. As I said, while operator classes originated in the context of indexing, they've now grown to affect several other parts of the system. Now I'm going to go through those. Probably the most prominent is order by, which uses typically B-tree operator classes. If you write order by X, the system looks up the data type of X, then looks up the default B-tree operator class of that data type, and then uses the comparison function specified by that operator class to put the values in order. There's also rarely used syntax to specify which operator class you want. That little swiggle there is the less than operator, the text pattern ops operator class. That is, when I say less than operator, it's listed as operator 1. You can sort of get the idea of why people don't like these alternate operator names, because they look pretty darn weird in your SQL queries.
I'm using Perl.
Yeah, well, after Perl, nothing really looks strange, right? There's a new way that operator classes can play a part in order by, introduced in 9.1, I believe, where an operator class can declare that if you have a query against an index column being applied to an operator, that the index is then able to return values in an order given by that operator. This was added to support k-nearest neighbor queries. So this is a k-nearest neighbor text search query, ordering by the similarity to a particular search condition. This is currently only supported by the GIST operator class, or excuse me, the GIST index access method, but that may change in the future. Another quite important use of operator classes beyond indexing is for equality comparisons. These come up in numerous parts of the system, things like union and group by. For example, when you're processing a group by and the system receives a new row, it has to decide, does this row belong with some existing group, or does this row start its own group? And if to make that decision, the system needs to effectively compare that value, the group key, to the group keys of existing groups. The way it does that is using an operator class, either a B-tree operator class or a hash operator class. Now, this is sort of invisible in many cases. One case where it becomes apparent that something non-trivial is happening is when you're dealing with a data type that can have values that are considered equal even though they are distinguishable. I'll give an example. The numeric data type, the values 1.0 and 1.00 are considered equal. And that's a good thing, because otherwise you'd have to say one of them is less than the other, and that would be silly. But they are distinguishable, and if you store them both in a column and check the bytes stored on disk, different bytes are in the disk for each of those values. Now, the B-tree and hash operator classes of the numeric type know this. They know that those values are equal even though they're distinguishable. And you see this in the result of this. This is a select distinct query, which is boils down to a group by. And as a result of those two being considered equal, we only get 2 rows in the output, 3 values in the output. Again, not actually a surprising result per se, but one of the things this shows is that if you have a data type that has this kind of situation where values are distinguishable yet equal, you need to be very careful about where you draw that line and consider 2 values to be equal, because that's going to have effect in all kinds of other parts of the system. It's going to affect group by, it's going to affect union. All these parts of the system that refer to your default B-tree operator class are going to make decisions based on that fact.
Question.
Yeah.
Right, is the, how is the numeric data type tagged so the system knows that it can't hash values to compare by quality? So,
I don't actually know how the system does that. I would get, it might just truncate the trailing zeros when it calculates the hash value, basically.
is that something in the hash of the hash function of numeric specifically? You think?
Yeah, the default hash op class of numeric is, specifies its own hash function that does more than just hash the raw bytes. You maybe
It
looking?
omits all the leading or trailing zeros from
Okay.
the input or to the hash.
Oh, so this is actually, yeah.
Yeah,
The reason I was thinking of that, we're talking, every so often we're talking about doing something with where we compare text fields for equality based on collation type things where different things could equal, they're equal, but that would break hashing, but I was
Yeah.
wondering how this is done, but this is not happening than that, so.
yeah, I think that is the difficulty in ever treating text values that are distinguishable as equal, because we need to come up with a hash function that knows how to represent that, that they hash to the same value.
Oh, yeah, okay, this is getting a little off track. I think,
Sure.
it was to hash the string transform of that.
Right, something like that. Unfortunately, the picture is not as clean as I just painted it, and that there are parts of the system that you might well expect to behave the same as things like group by and union, but they actually use the equal sign operator as opposed to using an equality operator. These include expressions like in and is distinct from, in case X when, also null if is in this category, in that you might expect them to be doing an equality comparison, but you actually just get the equal sign operator, whatever that may be. Now, this is sneaky because the most popular data types have an equal sign operator that is also their equality operator. So you don't notice the difference. A good test data type that exhibits the difference is the box data type. Box data type, geometric representation of a box. It has no B-tree operator classes, no hash operator classes. It does have an equal sign operator which compares area. So if you look at the first of these queries here, this first query uses select distinct, which uses the default B-tree or default hash operator class associated with box type. Oops, there is none, so the query just fails. Second example uses the in expression, and here you get an area comparison. So you notice neither of these queries have any operators in them at all, any like equal sign anywhere. So this is just illustrating how the things that are introduced through operators and operator classes kind of creep into other behaviors of the system. Other major thing that operator classes are used for is joins. So processing a merge join, that's only possible because the observation that the join condition, that's the bolded equal sign in that query, is a member of a B-tree operator class. Planner notices that, adds merge join to the list of things it can possibly do, also uses the comparison function to drive those sort nodes in the event that it actually chooses to do the merge join. Similar thing with hash join and default hash operator classes, or actually just hash operator classes in general. They don't have to be default ones. That's the exact same query as we saw in the previous slide. And here the hash operator class's existence allows that plan to be generated. hash indexes themselves, actual on-disk hash indexes, those have been deprecated for some time. However, hash joins are not going to be deprecated anytime in the academically foreseeable future. So almost all data types that include B-tree operator classes also include a hash operator class. If you're curious, for testing purposes, one exception to that is the money data type in the core system has a B-tree operator class, does not have a hash operator class.
Record also.
Not sure, maybe. So everything I've said so far has really been focused on the perspective of the system. What does the system do based on the operator classes that have been defined? Now I'm going to talk about what should your application do to make the right decisions based on what I've talked about so far. If there's one lesson I can drive home, one thing I'd like you to take away, it's that anytime you write A equal B, A equal sign B, that only has well-defined meaning if you know the data types of A and B. If you're using that as a template for values of unknown data type, behavior of that statement is not well-defined. At least the system makes no provision to keep that behavior well-defined. So in order to start doing better, you actually have to answer another question first. The question is, what equality semantics does your application really need? And the kind of applications I'm thinking of here are actually things like object relational mappers, caching layers, replication systems, things that deal with data types that the original authors may not have had in mind, may not have even had access to, because that layer of software is being deployed at a site that has its own custom data type written in-house. I've already talked about a couple notions of equality: equal sign equality, which you never want to use, B-tree or hash operator class equality, which is reasonable to use, used by many parts of the system. There's also kind of a third sense of equality that I call exact match equality. And this is only treating things as equal if they're in fact indistinguishable. In this world, 1.0 is not equal to 1.00. The system uses this in a couple of places. One of them is in the context of processing a row update. It uses exact match equality on the indexed columns to decide whether new index entries are required. That's the hot or heap only tuple optimization. It's also used in a couple places in the query planner, and it's used in materialized view refresh coming in 9.4. Now, the system actually implements that using a binary comparison of the data that would be stored on disk. But if you want to use exact match equality in your code, your application side code, you can do it by doing a byte-wise comparison of the output of the two data types. There are some caveats to this because there are some server settings that change the output of values, things like date style and extra float digits. So you need to make sure to set those in a disciplined way if you're going to do this kind of comparison, but that's how you can do it. And the question to ask yourself is, given this part of my software, do I want to treat 1.0 and 1.00 the same? So for example, if you have a caching layer and you're doing cache invalidation, you might want to err on the side of invalidation if you get values that are equal but distinguishable. Whereas in other cases, like something that's going to be tied to a primary key index, you might want to use operator class-based equality instead, so that you have the same semantics as the index you're mimicking. If among those choices, your choice is to use operator class-based equality, then there's a question of how do you actually look up the operator that you should use to do that. Now, if your code runs in the back end, there's a module called the type cache, which has a convenient API for retrieving it. The algorithm it used boils down to look for a default B-tree operator class. If one exists, use the equality operator of that operator class. Otherwise, look for a hash operator class and use its equality operator. You can implement that. You can implement that same algorithm in the front end using a system catalog query. David?
I ran into this problem with PGTap and I just ended up using is not distinct from. Does that basically do that lookup for you?
No, I believe it's not distinct from, just uses the equal sign operator.
Okay.
I'm pretty sure anyway.
That's surprising considering select distinct you said uses the
Right.
type class.
Yeah, that similar names, not similar underlying behavior here. The choice to use equal sign operators and things like is distinct from and in, I think was probably a mistake too late to fix. But I think if we were designing it all from scratch again, we'd probably be systematic and use one way to look this up. Do you have a question, Vic?
Well, the thing is distinct from is not an operator. It doesn't have an operator. So we can't use it like for any and things like that.
That's true, yes.
So
It's inconvenient, yeah, because
very.
I think that came up in the development of materialized views, right, Kevin? You wanted to use is distinct from. Right?
Yeah,
That's the
and
problem.
it wasn't appropriate because if the base table changed a value to something that was equal but distinguishable, the materialized view didn't change. So that's why the record image ops was created.
Sure, yeah. And finally, note that not all types have a notion of equality at all. XML doesn't, JSON doesn't. For practical purposes, you consider Box doesn't because it's equal sign operators and declared in any operator class.
But JSON-B does.
JSON-B does. That's a big step forward. Yeah. So whenever you're writing software like this, have a fallback plan, unless you're willing to just de-support anything that uses a data type that's not covered here, but there are enough of them that's worth having a fallback plan. Yeah.
When you say comparing the output, I've written something that does that by converting it, just casting it to text and then comparing. But is there a more efficient way to do that?
In something like PGCL code, I don't think there is.
You can
In
use
C code,
convert to binary, that's mostly more efficient.
convert to bind, but
To use the send routine. There's
Oh.
any send routine or something like that.
run it through the send function.
Yeah, that works.
Well, there you go. That sounds like a good idea.
Send?
So Postgres has two protocols for representing datums. One is the textual protocol and one binary. Most types have a binary representation that's faster to create. So, and you can use that to create a byte EA, and then you compare those, and that will often be faster, especially if they have like date time and floats. For those, it will be much faster.
And that's nice too, because it avoids the date style problem and stuff. So there, I learned something.
Thank you.
There's another side of this, the responsibility of folks who are implementing a data type. How should they set up their operator classes? So, as I said, it's important to pick carefully what your quality semantics are because they're going to affect everything. They're going to affect group by and array comparisons and all that stuff. Many data types that have sort of ambiguous choices in this area have actually declined to include any kind of comparison function to sort of not have to commit. I do encourage you to make considerable efforts to come up with a notion of equality for your data type, because without that you can't index, you can't group on it, you're pretty limited in many of the things you can do. So even if it's hard, try to come up with equality and define a default B-tree operator class. Once you've done that, you may as well include a default hash operator class. It's usually relatively simple at that point. Whether to use operator classes of other index access methods varies more on the nature of your type. For Gene, if your data type has the nature of being a container, like an array, or XML would also fall in this kind of category, that's a good clue to look at opportunities to add a Gene access method, or excuse me, a Gene operator class. GIST, it's a little harder to generalize about. From what I've seen, the development of GIST operator classes usually come from the opposite direction, that someone thinks up a new search strategy and says, oh, what data types is this search set strategy appropriate for, and then adds them. So I don't know how to give you a general rule about when the GIST operator class will help. That's the core of the material I wanted to cover. We do have some extra time and I have a bit more that I can cover, but I'd like to take a pause for any questions folks have at this time. Anybody? Okay.
And the real problem with things like JSON, that I'll try to put up my hand as being partly responsible for, is that there isn't a clear decision to make about what equality actually means.
Yeah.
Do you take into account white space? Do you take into account duplicated keys? Do you take into account key order?
Sure.
I mean, with JSON-B, all of that goes away, so we actually have a default operator class for JSON-B. But for JSON, it's, unless we, would we take the text representation? Would we canonicalize it somehow? What should
Sure.
we do? There just isn't an easy answer.
Yeah,
That's a great reason not to use JSON, isn't it?
Anyway, one moment. The technical operator for JSON is well defined,
Yeah.
but less or more, greater is not defined well because it's actually
Well,
hard to say which JSON is.
it's not necessarily intuitive, it's well defined.
Yeah, that's a good point. When you're defining that default B-tree operator class, it's okay if you're less than, greater than, or somewhat arbitrary if your type doesn't have a reasonable sense of comparison. You know, I think there are probably some other types in the base system that's the same.
The one that I created for the,
Record image ops.
record image ops, there's no ordering that makes sense there in particular, but as long as it's well defined, it works.
Sure, yeah. A few more things you can check out if you'd like to learn more about this topic. The first page I listed here is the core documentation for about the first half of what I talked about today. And it goes into more detail than I went into today. Great reference. If you'd like to learn about other other index access methods and how their operator classes are created, great reference is the ones we ship with PostgreSQL. Particularly for Gene and GIST, there are these contrib modules that re-implement B-tree in terms of those access methods. Those are great basic demos. If you'd like to see sort of what GIST is capable of, that you can't just redo with B-tree, the geometry data types have GIST operator classes that illustrate that pretty nicely. If you'd like to have a sense of how to write good client code, there's actually a piece of server code that I'd recommend looking at, namely the foreign key implementation. If you start at the server function called ATAT, foreign key constraint, you can see how it picks the operators that it will later use to consistently implement that constraint. I'll just quickly go through a couple other access methods, what their operator class looks like. Hash is the simplest of the access methods, always has one function, one operator. The operator is equality. The function is a hash function in the same sense that any computer science textbook discusses hash functions. A little more interesting is the Gene operator class. Gene operator classes have 4 mandatory functions. Another thing that always differs about them is almost always differs about them is the storage clause. Gene is targeted towards cases of objects that have substructure, an object that can be split into several what's called keys. So, for example, arrays. This is a mimic of the built-in operator class for gene indexing on integer arrays. The storage clause indicates the data type of the keys that are extracted from those input values. So start with an input of an array of integers, split it into keys. Each key is a integer. The architecture of a gene index is a B-tree of B-trees. The top level B-tree is indexed by keys, and each key is then associated with a B-tree of locations in the table that contain that key somehow. And there are some simplifications in the gene implementation for cases that have fewer keys, but that's the general case, B-tree of B-trees. Function 1 serves the exact same function that it serves in the B-tree access method. It compares 2 values of the storage type and is used to maintain that top level B-tree. In almost every case, you can simply use the same function 1 used in the default B-tree operator class of your storage type. Functions 2 and 3 are responsible for splitting an input value into its constituent keys, like splitting an array into the elements of that array, so to speak. The most interesting function is function 4, the so-called consistent function. This plays in that this function allows the set of operators supported by a gene operator class to be flexible, and not be understood in advance by the access method. So there can be any number of operators named in a gene operator class. You can have one operator, you can have a dozen operators. Gene itself has no preconceived notions about what operators will appear. It's actually this consistent function that's responsible for understanding all the operators that you specify in this operator class. So when a query is run and the planner determines that a gene index can satisfy that query, every time it wants to ask the question, is this particular search key consistent with this particular value in the index? That is, could this search condition return true given this particular search value and this particular index entry? Calls that consistent function, passes the ordinal of the operator that's being used in this particular search, and that consistent function is responsible for the logic of interpreting the operation represented by that operator. And this is kind of what I was talking about earlier about how you have considerably more control in the context of G. And that puts us about out of time. So any last questions? Well, I thank you for coming, and go enjoy Postgres.